Yes, another questions on electrostatics.
Şimdi hocam hani bu yan yana iki tane elektrik var ya, epsilon 1, epsilon 2. Biz şimdi şey demiştik, işte bu bir tanesine kuvvet ediyor, hareket ediyor demiştik. Bu ikisi şimdi birbirlerine doğru hareket etmeye çalışacak. Aralarında bir enerji aktarımı düşünüyoruz.
Well, you see, what we had done was we had looked at this problem. We said that, okay, to minimize the energy, this dielectric should try to move towards the right. Now, if you go back to this problem, where you have these two dielectrics, of course, if this first dielectric will try to move towards the right, the second dielectric will try to move towards the left, and whichever one feels the larger force, the whole system will move in that direction. So let's say if there is a larger force acting on the first dielectric with permittivity epsilon 1, the system will of course move in this direction. But then the first dielectric will be exerting a force on the second dielectric and hence doing the work. So you are saying that we have this system. Plus sigma. You put a dielectric inside, nothing changes. There is no electric field in between. Since there is no electric field in between, there is nothing to polarize this dielectric. You're done. Nothing changes. The electric field in these regions above the plates and below the plates will be just sigma over epsilon 0. There is no partial electric field. There is nothing like partial electric field. There is the electric field. And this dielectric will feel the electric field. Of course, that electric field can be written as the sum of the superposition of these two, the electric fields created by these two, but it will only feel the electric field. There is a single electric field. Of course, superposition principle does tell us that we can separate a given electric field into contributions from different charges in our system, but still the electric field is the electric field. There is a single electric field in the system.
Hocam bu elektriğe yük yapıştırabilir miyim böyle? Hani eksi yükü alıp yapıştırırsınız.
What prevents you? Just take a charged sphere, charge it, add some glue, stick it. Or, let's see. Your sweatshirt probably would be the best example. Just rub on it, it becomes charged, no? The charges cannot move around. Or your hair. Just rub a balloon on your hair. Both of them become charged. There are charges on them. They are not free to move around. And those additional charges that you put is what we call rho free and sigma free. Those are the additional charges we put to our system. Other questions? In this problem? Now the displacement is always epsilon 0 times E plus the polarization. If there is nothing to polarize, then the polarization will be 0, and so the displacement field is epsilon 0 times E. This displacement, this D field, let's say, let's forget about its name. This D field is defined everywhere as this combination. Forget about its name. So there's electric field. So there's this D field. Well, you see, it might happen that the polarization is equal to minus epsilon times E. I don't know if there are such systems. For such systems, you might end up having an E field but no D field.
Hocam böyle silindirik bir kapasitör düşünsen.
Okay.
Arasına da böyle bir elektrik koyuyor.
Okay.
Bir parça böyle. O elektrik o silindir içinde döner mi?
Why should it?
Yani üzerine kuvvet etki edince hareket ediyor dedik ya şekil için mesela.
Well, you see, in this example, let's do this minus 1. This won't feel any force. This dielectric will not feel any force. That one will because it is partially outside. This one is completely inside your capacitor and it won't feel any force, ignoring the fringing effects. To be able to have a force, if you move your system or the part of your system in the direction of the force, your potential energy should decrease. If there is no change in the potential energy as you move that part, there cannot be any force. You see, if you remember, that is also how we calculated the force acting on this one. We just assumed that we shifted slightly in one direction, calculated the change in the potential energy, divide by that displacement. That is what our force is. If there is no change in the potential energy, for example, in this one, if you just shift it slightly to the left or to the right, since this is completely inside the capacitor, there is no change in our potential energy. So delta U is 0, delta U over delta L is 0. So there is no force acting on this one. So if you have your cylindrical capacitor, if you rotate your dielectric slightly, there is no change in the energy of the system. So there cannot be any force. No more questions? Now, today we are starting our new topic, the magnetostatics. Well, it is still statics. Nothing apparent is changing, but different than electrostatics, this time we have things that are moving around. The charges in this case will be moving, but they will be moving at a constant velocity. They will not be accumulating at any point. Rho will not be changing. So this is, let's say, the definition of one of the definitions of magnetostatics. The rho doesn't change. The currents, we will be defining more precisely what we mean by the current densities. This will be 0. All the time, partial time derivatives of any property of the system will be 0. So that is what we will be meaning by statics. So if any time derivative is non-zero, it's no longer a static system. Now let's start with magnetostatics with an observation. You can have, for example, two wires. You can connect them to each other, and connect them to a battery, so the observation, so there will be a current running through it. The observation is that these two wires attract each other. Now, on the other hand, if you again take your wires, connect them to a battery, this time the currents are running in the same direction. These points are fixed. Then this time they repel each other. This is the observation. So now we have this new kind of force. Well, of course, you can claim that maybe the wires are being charged, but you can easily test that. Just bring another test charge from somewhere else. Take your test charge, bring them to these wires. They are neutral. You will see that they don't carry any electric charge. So there is no electrostatic force if they are not exerting electrostatic forces on each other. If they would be exerting electrostatic forces on each other, they would be exerting the same electrostatic force on this test charge, which they do not. So this is a new kind of force. Now, furthermore, this force is weirder than electrostatics, because if you remember, the force between two charges only depended on their position. But if you just take these two observations, the positions of the wires didn't change. Well, the force also in electrostatics, force also depended on the charges, magnitudes of the charges. Well, in this case, it apparently depends on the currents. But if you look at both cases, the currents has exactly the same magnitude. The magnitude of the currents also did not change. The only thing that changes is the direction of the current. So this new force has to be such that it also depends on which direction the charges are flowing. So that is another thing this force depends on. Now we will be defining a new field that we will be calling the B field. Then for a point charge, the total force acting on this charge will be Q times E plus V cross B. So this is the total charge, total force acting on a charge. This is the Lorentz force. Now this B field, well, I will call it with a slightly different name than your book. It is the magnetic induction. Now why I call it magnetic induction will be clear later on. So this is our new field. Well, you can basically think of this new field in this form. If you have a charged object that is moving in a region, it will be feeling a force. This force in general can depend on its velocity. There is nothing that says that the force should be independent of velocity. And it turns out that this force basically has two components. One part that is independent of its velocity, that is the part that we call the electric force, and another part that depends on the velocity, and that is the part that we call the magnetic force. Now let's look at some examples of particles moving under the influence of this magnetic force. For simplicity, let's start with assuming that there is no electric field. Well, in fact, before that, let's look at another case. What is the work done by this new force? Well, the work done is always F dot dl. You just integrate it over the path. This is equal to Q times V cross B dot dl. But the velocity of a particle is nothing but its displacement over a given time cross B dot dl. Well, the vector product of two vectors is perpendicular to both of them. So if you have an A vector over here, the B vector over here, A cross B is either pointing in that direction or pointing in that direction. Well, A cross B will be pointing in that direction. It is perpendicular to this B vector. It is perpendicular to the A vector. So dl cross B is perpendicular to dl. But if you have two vectors that are perpendicular to each other, their scalar product is always 0. So this is always equal to 0. Magnetic field never does any work. Well, we have a point charge moving. Q is the charge of the point charge. It is moving with velocity v. So for example, if you take a magnet, attach a metal to it, it will attract the iron. Not any metal, but iron it will attract. If you just lift it up with the iron, the magnetic field is not doing any work on the iron. So if there is no work, remember the work kinetic energy theorem. The work done on an object is equal to the change in its kinetic energy. So if work is equal to 0, the change in the kinetic energy is equal to 0. The total work done on an object. If the kinetic energy doesn't change, this basically means that speed is constant. So the magnetic field cannot change the speed of an object. It exerts a force on a point charge. It cannot change its speed, but it can change the direction of the speed. So that is what this force does. It will always change the direction of the speed of this point charge moving in it.
Ama mesela iki tane mıknatısı şöyle tuttuğunuz zaman bir tanesine yaklaştırdığınızda böyle yavaş geliyor sonra aniden çarpıyor.
Okay, there are forces. I'm not saying there are no forces.
O zaman hızı artmıyor yani giderken.
What is doing the work? So we will do some examples on that. You see, this is the total work done by the magnetic field only. There are no other forces in this system. If there are other forces on the system or there are other things that change, kinetic energy might change. This is only if there's only the magnetic force in the system. If there are other forces, of course, the total work will not be 0. But the work done will not be due to the magnetic field. Let's do an example. Well, let's look at wires. Let me take a wire. It is carrying a charge over it. So let me just consider this segment over here. There are charges moving. So let's say the moving charges has a charge per unit length of lambda. And they are moving with an average velocity, let's say v. So I will be equal to lambda times v. Y, let's say this is dt, this is dl. The charges are moving with velocity v. So the current is defined as the amount of charge passing through this point per unit time. That is how we define the current. I is equal to dq by dt. just keep in mind, this is not the derivative in general. This is not a derivative. This is not the derivative of Q because we don't have a function called Q in this system. Here, that dq is, you just count the charges passing through this point. That is what we call dq, in a time dt. And we will assume that it just, in that time dt, all the charges in this length dl passes through my system. So I can write this as dq by dl times dl by dt. Well, dq by dl is the charge in this segment divided by the length of that segment. That is the linear charge density. So this will be equal to lambda. Well, dl by dt, so if all the charges are moving at an average velocity v, after time dt, the charge at this point is passing through this point. So it covers a distance dl. It covers a distance dl in a time dt. So the distance covered divided by the time is nothing but the velocity or the speed. So this is why the current is equal to lambda times the velocity, lambda times the speed. Now let's assume our system is in a magnetic field. Some magnetic field. The force acting on this very small segment will be the total charge there. That is dq. They're all moving with the velocity v cross b. This is the force acting on that very small segment, this segment. Let us rewrite this in this form. dq by dl times v times dl cross b. Now dq by dl is nothing but lambda. Lambda times v dl cross b. Now I will define a vector along this wire. You see, v is along the wire. I will define another vector along the wire and I will call it dl vector. So this vector is my dl vector. So v dl is actually v dl. dl. I divided by dl multiplied by dl. I said that the total charge of this segment is dq. They are moving with velocity v. So this is the force acting on them. I divided by dl multiplied by dl, so that dq by dl is my charge density. Now I'm just, v is, let's say, in that direction. So it's the magnitude multiplied the unit vector in that direction, but that direction is along my wire. So I just define this dl vector along my wire. So both v vector times dl and v times the speed time, the velocity times dl, and the speed times this dl vector, they are both pointing in the same direction because of my definition of dl. dl is along the wire, v is along the wire. So they are pointing in the same direction. They both have the same magnitude, so these two are equal. So this tells me that the force acting on my system is just lambda v times dl cross b, but lambda v is nothing but my current. Just keep in mind that dl vector over there is a vector that I define along the wire, and it is in the direction of the current. So if the current is, in this problem, this is the direction of the current. And at this segment, this will be the direction of dl. Parallel to the wire in the direction of the current. So in particular, if B is constant, uniform, and L wire lies on the plane perpendicular to B. Let's say the B field is into the screen. And this is our wire. DL and B, they are always perpendicular to each other, so the angle between the two is 90 degrees. So the magnitude of DL cross B will be equal to the magnitude of DL times the magnitude of B times sine of 90 degrees. This is B times DL. So the force, let's say this will be the integral of I dl cross B. What is the direction of the force? In the top segment. This is dl. B is into the screen. dl cross B. At this segment, it is pointing upward. In this segment, it will be pointing in this direction. In this segment, it will be pointing in this direction. Let's say this length has total length A, that segment. Well, all of these, on the left and on the sides, they will just cancel each other. So what is left with the contribution from that part, all of the segments, the force acting on them, they're all pointing in the upwards. So the magnitude of the force will be just I times A times B. Because remember, I'm assuming that B is uniform, B is constant, so I can just take it out of the integral. I is constant. So this will be equal to I integral of dl cross B. I took B out of the integral. And that sum of dl vector is nothing but this vector pointing from this corner to that corner. So the magnitude is just this one. Now this is the question to start with. Let's assume we have some mass m over here. Now, if we have this mass m, what is, let's say, for a given magnetic field, what is the current that would create the force sufficient to hold this mass m mid-air? Now, we know the total force. The total force is I times A times B. This is in the upward direction. This should be equal to the weight of the object. So the current, let me call that current I0. This is mg over AB. So if there is such a current running through my wires, then the force acting on my wire will be sufficient to hold this mass m stationary. Now let's see, for I larger than I0, what will happen if I run more current through my wire?
F will be more than
the weight.
Yeah, more than the weight, so it will go
It will go up. So there will be a force in the upward direction. It will accelerate up. And this mass will gain kinetic energy. Right? So there is this force, which is apparently due to magnetic field, which is apparently doing some work on my mass, changing its kinetic energy. Right? So you see, what we said just before, which you were objecting, he was objecting, you were objecting, when I said that magnetic field does not do any work.
What is doing work here is the changing current, not the, I mean, the change in magnetic field, changing current.
Well, the current is constant.
So the changing.
I am sending constant current through my system, which is larger than this one. And since the current is constant, there is no change in current. The current is constant, but my system, we just said that the force acting on the top wire will be vertical. It will be larger than the weight of my mass m, and hence this mass m will be accelerating upward. So there is work being done on my system. So, well, there is this force F upward. My system is moving upward. Force in the direction of displacement. We are doing work. No, it's outside the magnetic field. Sure, it will do that. But for the time being, it's outside my magnetic field. Because there, you see, at this time, at this instant, the upward force is larger than the downward force until this side enters the magnetic field. Until that time, at least, my system is accelerating. So there is work done on my system. And I still stick to my claim that it's not the magnetic field that is doing the work. So we should do something else that is doing the work.
What about the downer edge of the square? Right?
Yes, that's what she was asking. That side is out of the magnetic field. At least at this time, the force is vertically upward, the system is accelerating, my system is moving upward, so F is doing work on my system. F is, we said, it is created by the magnetic field.
There may be an induced magnetic field.
No? Let's see. Okay, let's just do the calculation. Now, we said that there is this current running in that direction. What is the velocity of the moving charges? Let's say it's the charge density is lambda. We said I is equal to lambda times V. Right? But keep in mind, this is moving upward. So my charges are not moving horizontally anymore. They have a slight inclination. So they are moving in this direction. And they are moving horizontally with velocity v. And let's say they are also moving vertically upward with velocity u. Because my system is accelerating downward. In the rest frame of my wire, the charges are moving with velocity v. And then I'm just also moving them with velocity u upward. Do you agree? Is v over here or over there? I have my wire. In the rest frame of the wire, the charges are moving with velocity v. And then this wire is moving upward at a given instant with velocity u. Do you agree? Do you all agree? So is this v or is this v? Which one is v?
Çünkü yüklerin hareketi değişiyor ki kabloyu sadece.
The total is v or the horizontal is v? Let's stick with this one. Are you sure?
The horizontal should
Yeah. So let's see. This is the total velocity of my charges. Now the force acting on my charges is perpendicular to V prime, not to V. So this is the force acting on my charges. You see, remember, the force, the Lorentz force is QV cross B. If we have a point charge with charge Q, it is moving with velocity V. This is the force acting on my charge, which is perpendicular to V and also B. So if this is the velocity of my charged object, this is the force acting on them, perpendicular to their velocity. Well, this force has two components. The vertical component and also the horizontal component. Do you agree? Now, if my charges are to be kept moving along the wire, something should be pushing my charges against this horizontal component. What is pushing it against this horizontal component? It's basically the battery. Remember, to create this current, we should attach a battery to our system. And unless the battery pushes my charges against this horizontal component, I cannot keep the current running in my wire. This is not due to the resistance. I mean, the battery should overcome the resistance. It should do work against the resistance, any resistance in my system. Now, if the wire is moving upwards, now the battery has to do more work to counteract this component of the velocity. In fact, well, not today, but on Friday, we will calculate the work that the battery has to do to counteract this component, and we will show that it is actually the work done on this wire. So it's not the magnetic field, but it is the battery that is doing the work.
But before applying the new current, we also had a battery that was creating I0.
So you have to increase the voltage to create a higher current. But as the charge is, as the current is increased, as the wire is accelerating, this just tells me that, you see, if it is accelerating, it just means that the work that you do in a given amount of time is getting larger and larger because the work done is force times the displacement. If it's moving faster and faster, the displacement in a given amount of time is also increasing. So there's more work done in a given amount of time. But so you have to turn on the battery more and more. The voltage should increase more and more to keep the current constant. An example in your book that is nice is, just look at this problem. You are pushing it horizontally. There is this normal force which doesn't do the work. The normal force is always perpendicular to the direction of the displacement. So the normal force never does any work in this case. It's always you are doing work, but you see the system moves upward. You are not doing any work upward. You are not pushing it upward. You are pushing it horizontally. What the normal force does is, in a sense, it rotates the force that you apply. You apply a force in this direction, it causes a force in the vertical direction. That is what the normal component does, just like in the case of the magnetic field. The magnetic field never does any work, but it converts. You see, the battery should be exerting this force, which is creating a vertical lift of the wire. So it causes the force of the battery to kind of change its direction and hence do the work.
O zaman biz neden kuvveti yukarı doğru gösterdik?
Because it is what, you see, this is the force acting on a single charge, not the wire. The force acting on the wire is, sorry, this will be balanced by the force acting by the wire, by the battery. So the force acting on the charges will not be only due to the magnetic field. It will be the magnetic field plus the battery. Both will be exerting a force on our charges. The sum is vertically upward. The sum is given by our previous expression over here. By this expression over here. Now we will pick it up from here and continue on Friday. And just a reminder about the recitations. I mean, just if you want a recitation tomorrow, make sure to click yes in the do you want a recitation question in Not the Class. Also vote on which date you want the homeworks are to be due.